Well, thanks for the introduction. It's great to be here. Appreciate the invitation from Professor Yao and Dan to give this colloquium. So there was actually more than one version of the abstract for this, because originally I was going to be speaking in a differential geometry seminar where I was going to talk about asymptotics of hyperkaehler metrics on moduli spaces. So if that's what you came for, please do find me after the talk or tomorrow. I'll still be here if you want to ask me questions about that. But this will be colloquium style. It's just very general introduction and broad overview about these topics, Higgs bundles and the Hitchin system. Some of you in this room will know a lot about this topic. For those of you who don't, this will be sort of a soft introduction. Okay, so the main object in this talk is the moduli space of Higgs bundles, which you can think of as, or at least developed a role over time as a bridge between geometry, differential, symplectic, and algebraic, representation theory, and physics, physics being where it originated in the work by Hitchin and others in the early 1980s when the kind of mathematical geometric investigation of gauge theory began. So specifically, this moduli space was discovered, if you like, by Hitchin in 1987. So the basic starting ingredient here is a Riemann surface.
Where was that paper? Hitchin's paper, I forgot. Where did it appear?
Oh, the 1987 papers, the self-duality equation.
Yeah, no, where was that? Where did it appear?
Oh, in Proceedings of the LMS. That's where it was, yeah. There's another related paper at the time, Stable Bundles and Integrable Systems, on the same topic that appeared in these two papers, I think. And so the basic ingredient that we begin with is a Riemann surface. You can take it to be as nice as you like, compact, connected, smooth, and typically of genus at least 2. And then the standard notation is we can let fancy OX be the trivial line bundle on this Riemann surface, and omega x, or sometimes kx, will be the holomorphic cotangent bundle. The line bundle whose sections are the holomorphic 1 forms on the surface. And we'll fix integers r and d are greater than 0. And then now that we fixed this data and numerics, the Higgs bundle is a pair of a holomorphic bundle E of rank r and the degree d that we chose, and a holomorphic map, we'll call it phi, from E to itself, so it's almost an endomorphism, but twisted by omega. So it's an endomorphism, it's a self-map of phi that's one form value. And that's usually called a Higgs field, an extra piece of structure. You can think of the Higgs field as an element of H0, so H0 denotes global sections, global holomorphic sections of endomorphisms of E twisted by or tensored by omega, or you could think of that as E dual tensor E. So those are maps from E to itself, tensor omega. So there's different ways to think about where this map lives. So perhaps the simplest example I could pick for you is to take E to be L, some holomorphic line bundle, in which case the Higgs field phi is just a 1 form on X. This is because endomorphisms of L are L dual tensor L, which is the trivial line bundle, which goes away, and so you're just left with a 1 form. So this is, you could think of as an abelian example, where you can form a non-abelian example. Maybe the classic non-abelian example would be to choose any square root, omega 1/2, of the cotangent bundle, take the direct sum with its dual. Okay, so now you've formed a rank 2 bundle, and then take a Higgs field that looks like that rank 2 matrix, where the 1 means exactly what you think it is. It's literally the number 1, okay, acting as the identity, but alpha is a quadratic differential. So this is This is a point in what's sometimes called the Hitchin section. So this is probably the most famous example of a Higgs bundle. Now, some basic algebraic properties. If you have two Higgs bundles, E phi and E prime phi prime, you'd say that they're isomorphic if and only if there exists a bundle isomorphism, first of all, we'll call that psi, from E to E prime, such that the following diagram formed from psi and two Higgs fields commutes. So it's what you would expect from linear algebra. And throughout this, you can just think about E as a vector space, if you want, and phi as a linear map from that vector space to itself. But somehow we have a big family of these things parameterized by the Riemann surface. So most things that you think of in linear algebra actually hold for these things. It just justifying them takes a little bit more care. Now, to see how these things arise in the gauge theory, what you want to do is fix a smooth rank R bundle E of degree 0, so it doesn't have a holomorphic structure, and up to isomorphism there's only one. And then what we want to do, or this is what Hitchin did in '87, is consider the space of solutions of the following equations. The first one is, okay, so these are pairs of a connection, a unitary connection A on the smooth bundle, and the smooth map phi from the smooth bundle E to itself, valued in the one forms. And then we ask for these to be solutions of these equations. So we want the curvature of the connection A plus phi adjoint. The adjoint is taken with respect to a Hermitian metric compatible with this connection. We want that to be 0. So in a sense, this phi dual conjugate here is the obstruction to A being flat. And the second equation you could just say is phi being holomorphic with respect to the complex structure on E that's induced by this connection. So we take all of these pairs A and phi up to gauge equivalence, and we get a moduli space of solutions. So the SD, I'm going to call this MX, X for the choice of Riemann surface, R for the rank, 0 because I'm talking about degree 0. SD here is, because these come from the self-dual Yang-Mills equations, but they've been dimensionally reduced. Sometimes these are called Hitchin equations. So they're a two-dimensional version of the usual self-dual Yang-Mills equations. And there's a way to incorporate arbitrary degree. Instead of having 0 in the end of the first equation, there's a term that you can introduce involving degree. So a solution of these equations is precisely what we defined earlier to be a Higgs bundle. So for rank 2, these equations were studied in this 1987 paper of Hitchin that I referred to, where generalized arbitrary rank and actually arbitrary complex smooth projective varieties X by Simpson, I guess beginning in '88 and then following on with the sequence of papers through to about 1994. So this is sort of the gauge theoretic origin of Higgs bundles. And what's interesting is that a pair E phi solves the Hitchin equations if and only if for each proper non-zero subbundle U of E, with the property that U is invariant under the Higgs field. Again, just think linear algebra. Okay? I want to look at invariant subspaces. But what is invariant here? Invariant means invariant up to the twist by omega. So it turns out that E phi is a solution of the equations if and only if for all non-zero proper phi invariant subbundles, we have this condition that the normalized degree of U, the degree over the rank, sometimes called the slope, must be less than or equal to the degree of E over the rank of E. So the slope of a subbundle, of an invariant subbundle, must be less than the slope of the bundle. So this was found in Hitchin's paper again, but then later generalized arbitrary rank. But in a sense, it reduces this problem to linear algebra, okay, in families again. So again, this is a colloquium, and you can take as much detail from it as you want. So depending on how the level of interest you have in figuring out these details, an exercise would be to maybe show that this classic example is a solution of the Hitchin equations by showing that it satisfies this inequality. And I guess the key hint here is that there are no invariant subbundles. So you can reduce this exercise to showing that there are no proper invariant subbundles. And then it's really just the fact that your matrix is only has entries on the anti-diagonal. Okay, so I just gave you the entire answer. So I'm being generous. Okay. It's a simple exercise. Now, alternatively, instead of by gauge theory, you could construct a moduli space of isomorphism class of Higgs bundles using what's called GIT, or geometric invariant theory. So this is an algebraic procedure for producing quotients with nice topological properties. I guess first developed by Mumford. So the typical situation would be a vector space V with an action by some group G. So the quotient topology on the set theoretic quotient V, just V mod G, is generally not Hausdorff. Okay? You'll have bad orbits, okay, that are too close to other orbits. So GIT is a procedure that produces a quotient, often denoted V double bar G, which is the usual quotient V mod G, but minus certain unstable orbits which are discarded. So GIT is the procedure by which you decide that some orbits should be thrown away. So the classic example would be C star acting on C2 by rescaling. We all know that we have to throw away the origin, and that's what GIT tells you to do. And then what you get is the Riemann sphere. So that's the GIT quotient. V and G, in fact, need not be finite dimensional. Okay? And it's possible that even in this case, V mod G may still be finite dimensional. And it turns out there exists a moduli space, we'll call it MGIT, parametrizing semistable isomorphism classes, semistable being the opposite of unstable. Stable is not quite the opposite of unstable. We'll call the opposite of unstable semistable, because there's some borderline cases. So GIT tells you to throw away some bad orbits, some bad Higgs bundles, and keep the ones that are declared semistable, and you get a resulting moduli space. So this was constructed by Nitsure in 1991. It was for arbitrary rank and arbitrary degree. And the beautiful thing is that it turns out that the stability condition given to you by GIT is exactly being a solution of the Hitchin equations from before. Okay, so in other words, the stability condition is the stability condition involving the inequality on slopes that we saw earlier. So in fact, we'll just talk about the moduli space M, which is MGIT or M self-duality, depending on which point of view you want to come at it from. But it's not so surprising because there is a certain sort of nice class of problems in which GIT quotients and so-called symplectic quotients or Kähler quotients are really the same thing. And this is an example of that. So the GIT quotient here is isomorphic to the Kähler quotient for the moment map consisting of the left side of the first Hitchin equation. And this is a moment map for the action of the gauge group on the space of solutions. This happens to be a smooth manifold or non-singular variety when the rank and degree are coprime. Otherwise, it has semi-stable but not stable points, which are orbifold points. Okay, so a related object, maybe somewhat simpler, we'll call it UXRD, is the moduli space just of holomorphic bundles on a Riemann surface with no Higgs fields, none of the phi data. This can also be constructed as a solution space. You could think of it as, well, there's no phi's anymore, so we're just asking for the curvature to be 0. This is really the correspondence of Narasimhan-Seshadri between bundles, degree 0 bundles with flat connection and holomorphic stable bundles, so that's the GIT coming in. And here it's the same stability condition as earlier, but we're checking all proper subbundles, which is what you'd expect because we really have the 0 Higgs field, and so all subbundles are invariant under phi. Okay, so this is all consistent if we go to this case. Now, a question I want to ask is, what is the tangent space to the moduli space of bundles at some bundle E that we pick? Some stable bundle E? Well, according to deformation theory, the first order deformations of the holomorphic structure on E are parameterized by cohomology classes in H1 of endomorphisms of E. So that's the tangent space at E. Well, if I want the cotangent space, I'm going to dualize this, and that's what Serre duality tells me. Serre duality says that the dual of this is in H0 of endomorphisms of E, and E is self-dual because E star tensor E goes to E tensor E star, but we have to include the dualizing sheet, which happens to be the cotangent bundle. Well, this you'll recognize is exactly the space of Higgs fields. So the cotangent directions are the Higgs fields for E. So, in other words, the cotangent bundle to the moduli space of just bundles is contained inside the moduli space of Higgs bundles. And I say contained because there could be Higgs bundles which, when I forget the Higgs field, the bundle that's left over is unstable. So it may not project down to the moduli space of just bundles at those points. In fact, we only have equality when R is equal to 1, when we have Line bundles. When the rank is bigger than or equal to 2, as I said, there are semi-stable Higgs bundles for which E is not semi-stable as a bundle. Nevertheless, the containment is open-dense. So two places where this is done are the original paper by Hitchin for rank 2, but also the paper of Markman on spectral curves from '94. So again, here's another exercise. Show that the dimension of the moduli space of bundles is the rank squared times G minus 1, where G is genus, all plus 1. And my hint is use Riemann-Roch. So I already told you what the tangent space is as cohomology, space, so you just need to figure out what the dimension of that is. And for that, you can use Riemann-Roch, the Riemann-Roch theorem. So then, by this open dense containment, the dimension of the moduli space of Higgs bundles must be twice the dimension of the moduli space of bundles. So the open dense containment of the cotangent bundle inside the moduli space of bundles. So that gives us the dimension of the moduli space of Higgs bundles. Now, we know that there's equality in this when R is equal to 1, so certainly that means that when R is equal to 1, the moduli space of Higgs bundles is non-compact because it's a cotangent bundle of something. Okay, but naively one could ask for rank greater than 1. Is the moduli space of Higgs bundle some sort of compactification of the cotangent bundle? Well, to answer that, there's another way to view the moduli space of Higgs bundles as a fibration. What you do is you can define a natural map H from the moduli space of Higgs bundles down to some affine base consisting of different powers of sections of the cotangent bundle. And really what this map is, it just takes, again, linear algebra, it just takes a Higgs bundle E phi and gives you its characteristic polynomial. The characteristic polynomial for a twisted endomorphism like this is going to have coefficients that take values in powers of a line bundle. So it turns out that this map is proper, and for rank 2 by Hitchin and then later by Simpson, at least the original arguments by Hitchin used sort of weak compactness style arguments like was found in the works of Uhlenbeck and Yao in the mid-80s. So from this map, we get what's called the Hitchin fibration. So the fiber of this map H you can think of as a moduli space of semi-stable Higgs bundles, but with a fixed characteristic polynomial. So let's analyze that picture. So let's pick a generic characteristic polynomial rho in the base. Okay, so if it's chosen generic, okay, then the eigenvalues of any Higgs field phi with that characteristic polynomial will have multiplicity 1 at all but finitely many points in the Riemann surface. And so the eigenvalues themselves will form a generically R to 1 cover, R being the these Higgs fields are R by R, so these eigenvalues will form a generically R to 1 cover, we'll call it X sub rho, of your original Riemann surface, called the spectral curve associated to rho. So this is a ramified R to 1 cover. The eigenspaces will be one-dimensional, again, generically, and you can show that they form a line bundle over the spectral curve. So two phis with the same rho will differ only in their eigenspaces, and so in a sense, the fiber of this map, H over rho, is parametrizing the different eigenspaces that you can have, which means it's parametrizing these different line bundles over the spectral curve. So this leads to, informally, this leads to an identification of the fiber over rho with the Jacobian of line bundles over X rho for some degree d prime, which is generally not d. So ramification will sort of mutate the degree that we started with. We may lose vanishing points of sections, etc. So, in other words, since we've identified the generic fiber with the Jacobian, that's saying that the generic fiber is a complex torus of dimension G tilde, which is the genus of the spectral curve. It also turns out that the dimension of the base of the Hitchin map is exactly half the dimension of the moduli space of Higgs bundles. You can get that just by looking at the dimensions of these spaces of powers of the canonical line bundle, add those all up together, subtract them from the dimension of the whole moduli space, and you get that it has 1/2 the dimension. But that means that the generic fiber has 1/2 the dimension of the moduli space. And so that tells you what the genus of the spectral curve must be. It must be r squared times g minus 1, all plus 1. In fact, so the moment you see that this is half-dimensional, you can ask what kind of torus fiber, and that it's tori, that this is fiber by, you can ask what kind of torus vibration this is. It's a complex Lagrangian torus vibration with degenerate fibers. So at that point, if you're interested in mirror symmetry, you can ask, does this fit into Strominger-Yau, Zaslow type mirror symmetry, which is something it does actually, and it's something we'll address a little bit later. So that's sort of one direction you can start thinking in the moment you see this. So okay, exercise 3. Going back to here, try and find an expression for the degree d prime of the spectral line bundles in terms of the parameters r, d, and g tilde, the genus of the spectral curve. It's more Riemann rock type calculations here. Now, another feature of the modular space of Higgs bundles is that it comes with an action, a natural action by C star. So C star will leave the bundle E alone, but will rescale the Higgs field phi. So when I do this, the determinant, of course, of phi will transform as t to the r times the determinant, etc. So you can see how the characteristic polynomial changes. And as long as the characteristic polynomial of phi is not 0, this means that the C star action will move your Higgs bundle E phi from one fiber of the Hitchin map to another, because it's changing the characteristic polynomial. And in fact, I can take t to, well, modulus of t to infinity. And so you can see that there are infinite directions in this moduli space, so it's not a compactification of the cotangent of u for any r. Okay, so this is actually, this moduli space is non-compactable. So it looks something like this. Okay, so if I had to draw a cartoon of the moduli space, it would be something like this. The generic fibers are tori, there are some degenerate fibers. The fiber over 0 is always highly degenerate. It's the most degenerate fiber. Those consist of the nilpotent Higgs bundles, and it's over this flat affine base of characteristic polynomials, so flat in every direction, kind of like Saskatchewan, where I'm from, or where I'm based at the moment. So that's a picture of just outside Saskatchewan. There is a university, it's just not in the picture. There is a torus vibration over Saskatchewan. And actually, this C star action is highly useful. So the cohomology of the moduli space turns out to be exactly the cohomology of the fixed point locus of the C star action. So there's different ways to justify that. From a more differential point of view, it's really just Morse theory for a Morse function that was really just the norm of the Higgs field with respect to the metric on the moduli space. So that's a moment map for a circle action contained inside the C star, or more algebraically, it's Bialy-Dixky-Barula theory. There's different ways to think about it, but the point is you can compute the fixed points of that C star action, and actually the cohomology of the fixed point locus is precisely the cohomology of the moduli space. And as we said, the action will always take you from one fiber to a different one unless the characteristic polynomial is 0. So the fixed points must be contained in the fiber over 0. So in fact, only nilpotent Higgs bundles can be fixed. And then you can ask, are all nilpotent Higgs bundles fixed? Well, no, they're not. Only special ones are fixed. These are what are called complex variations of Hodge structure. So they have a special form. You could think of them as representations of A-type quivers, but in the category of coherent sheaves on your original Riemann surface. So they're quickly get into some technical details there, but the point is we can use this in principle to find, say, Betty numbers for the cohomology of the moduli space. But this is very, very difficult in general. So Hitchin did this for rank 2 in 1987. Goten did it for rank 3 in 1994. Rank 4 wasn't done explicitly until 2011 by Garcia Prada, Heinloff, and Schmidt. And I guess now it's sort of been done in general by completely different techniques by people like Moscovoy and Schiffman. And I think people are still trying to understand that to some extent. But this is, in some sense, finding explicit Poincare polynomials for the moduli space of Higgs bundles for increasing rank is a 30-year-old problem. It turns out that the Poincare polynomials are independent of D, and there are reasons for that, which are somewhat technical. But this is a very hard problem, at least from the point of view of Morse theory. Okay, so there are other interesting features of this moduli space. We've only really started getting to the heart of things. There is, of course, a symplectic form on the cotangent bundles of the moduli space of just bundles. And it turns out this extends in a canonical way to the moduli space of Higgs bundles. It turns out that this Hitchin map H, this characteristic polynomial map that we defined, its components are algebraically independent and Poisson commuting functions. If I take its components individually, they commute with respect to the symplectic form. And so this actually makes the moduli space of Higgs bundles into an algebraically completely integrable Hamiltonian system. So the total space of this moduli space is actually a dynamical system. So again, this came in Hitchin's other paper from '87 called Stable Bundles and Integrable Systems. So you can ask, do we recover any known integrable systems from this construction, or is it somehow completely new? Well, to answer that, one thing you can do is try and extend the system to low genus, particularly the sphere, genus 0. And you can do that in a couple of ways. So the issue with the sphere is that it has no holomorphic one-forms, as we know. And as a result, the moduli space of Higgs bundles on the sphere, just defined in the usual way, has only semi-stable but not stable points. That's quite a degenerate moduli space, at least when rank is greater than 1. There are two ways to fix this. You can take Higgs fields that have values in some line bundle of sufficiently high degree, not the cotangent bundle, something else. And this will produce for you a moduli space of matrix valued polynomials. So this is sometimes called the Beauville system. And from this, you do start seeing some classical integrable systems such as Nom's equations for monopoles. Another thing you can do, which is maybe more common, is you can puncture P1 and introduce Higgs fields that are valued still in the cotangent bundle, but have residues that respect fixed flags of the puncture. So this is a parabolic Hitchin system. From this you can recover Calligaro-Moser and some other classical systems from this picture. So So at least definitely in genus 0, you see classical integrable systems arising as different instances of the Hitchin system. And then for the genus G greater than 2 system, it in a sense reveals new integrable systems, but they're of the KP or KDV type, the KDV hierarchy. So it's just new instances of these families of integrable systems.
What about genus 1?
That's a good question. So genus 1 gets ignored in the theory of Higgs bundles, mainly because in genus 1, the cotangent bundle, of course, is trivial. You know, it's a one-dimensional Calabi-Yau manifold, so you have this. So that means that the Higgs fields phi just go from E to E. They're just endomorphisms. So for that reason, I think they're historically ignored. And also, they don't come up naturally in the gauge theory, at least for the Self-Yang-Mills equations. But they have been studied more recently. So there's Oscar Garcia Prada and his students recently have studied the elliptic curve case. And then the elliptic curve with punctures, I think, was studied in a paper by Bensby and Nevins, I think, at some point. And so they studied the integrable system that comes in that. So there is, I can't tell you what type of integrable system it is, but it has been studied in at least one paper. Any other?
It's Bensby and who?
Nevins, I think. Definitely Bensby. So, and then, you know, that gives a new meaning to the tori that you see in the picture of the Hitchin vibration. They're Liouville tori for the dynamical system. And in fact, you can get lax pair equations for this dynamical system. So these are equations of the form d phi t by dt. So we're looking at the time evolution of a Higgs field, okay, say along some lines, so some linearized flow along one of these Hitchin fibers. So having a lax pair equation means you can write this time evolution as a commutator of phi and some other matrix C. So you can actually explicitly find this matrix in some cases, particularly for the Beauville system in genus 0. So there are these notes of Hitchin, Ward, and Siegel. I think in chapter 1 of that book, they compute C explicitly in the case of genus 0. So I mean, having a lax pair equation is kind of a holy grail in dynamical systems. It's like you know everything you need about the system if you have a lax pair equation. So we can do that here. Okay, and then now let's impose this condition finally of the rank and degree being co-prime. So this will ensure that the moduli space is smooth. And let's go back to genus greater than or equal to 2. So it turns out that underlying this picture, there is a smooth manifold, we'll call it H, or HXRD, whose real dimension is 4r squared g minus 1 plus 4. So complex-wise, it's the same as the moduli space of Higgs bundles. And this smooth manifold admits a trio, or triple of complex structures, I, J, and K, we'll call them, and a Riemannian metric kappa. I don't want to call it G, because I need G for the genus. Okay? Such that the following happens. I, J, and K satisfy the quaternion relations, and thereby define an S2's worth of complex structures for H, for H. So we can form complex structures AI plus BJ plus CK, where A squared plus B squared plus C squared is equal to 1. So this will also be an integrable complex structure, and so they give you points on a 2-sphere. Okay, so we have a sphere's worth of complex structures. And I, J, K are covariant constant with respect to kappa. So we refer to I, J, K, and kappa collectively as a hyperkaehler structure. So hyper meaning 3 Kaehler structures or complex structures. And what happens is if I equip this manifold HXRD with the 0 complex structure, if I look at this as P1, if I look at my sphere of complex structures as P1, and let's say that the north pole is 0, then what we get is the moduli space of Higgs bundles. So you could think of there's this big non-compact smooth manifold of this dimension sitting over here. And I have this sphere and I'm putting my finger at different places and choosing different complex structures for it. When I choose this complex structure at the north pole, it becomes the moduli space of Higgs bundles that we've been looking at. And then if I take some other point away from the north pole, any other point, it becomes a moduli space of flat or projectively flat if the degree is not 0. Irreducible connections on a smooth rank bar degree D bundle on our Riemann surface. Or another way to think of that is as irreducible or twisted irreducible representation if the degree is not 0 of the fundamental group of the Riemann surface into our structure group for the bundle, which is GLRC. So if I pick here, I get Higgs bundles. If I pick anywhere here, this actually becomes a moduli space, but not of Higgs bundles, of flat connections. You could ask what happens if I pick the south pole and it becomes a moduli space of anti-holomorphic Higgs bundles. So with respect to the complex structure on the Riemann surface. You can think of the moduli spaces you get from here as inheriting complex structures from the Riemann surface, whereas these points in here inherit complex structures from the group. And that's where you get representations of pi1 and 2 in the group. So the implication here is that, well, there's this underlying smooth manifold that's staying constant. So the Higgs bundle moduli space and the moduli space of flat connections are diffeomorphic, not complex analytically isomorphic, okay, because these are literally different complex structures. And then this diffeomorphism is one aspect of what's called non-abelian Hodge theory. So because we have this hyperkaehler structure, it turns out that hyperkaehler implies Calabi-Yau. So the Higgs bundle moduli space is a Calabi-Yau manifold, albeit a non-compact one. So we can hyperkaehler rotate, which just means picking a different complex structure on the sphere. We hyperkaehler rotate our Hitchin fibration to some non-zero complex structure, and the fibration then goes from complex Lagrangian to special Lagrangian. So we really are now in the framework of SYZ, Strom-Yau, Zaslow mirror symmetry. So then the question is, does this manifold HXRD with some phi not, or some zeta not equal to 0 have mirror symmetry? So to see how this works out, we should go to principal G bundles instead of vector bundles, instead of GLR bundles. So most of the discussion carries over if we replace vector bundles with principal bundles. And then, so we'll have HX comma G be the corresponding moduli space. So we'll let the subscript, or the superscript actually, zeta, indicate the hyperkaehler rotation of the moduli space of principal G Higgs bundles to a special Lagrangian fibration. And according to Hausel-Thaddeus and Donaghy-Pantev in different papers, the mirror of this guy ought to be the manifold HX LG RD, that choice of complex structure, where LG is the Langland's dual group of the group G. So this is why we had to switch to an arbitrary group, because GLR is self-dual under Langland's duality, so you wouldn't see this. But if I switch to a group like SLR, then the Langland's dual will be PGLR, and you will see the change. So there is an SYZ style mirror symmetry for the Hitchin system, and it's wrapped up with Langland's duality, which is, again, another sort of fascinating thing, that all of these things are converging in this one moduli space. So as I said, GLRC is autodual, but the classic example would be SLRC, and its Langland's dual is PGLRC. That's exactly the case that Hausel and Thaddeus investigated. So a topological test for mirror symmetry then could be carried out with the original non-rotated spaces because they're diffeomorphic. So in other words, mirror symmetry has topological implications, but I can, instead of working with the special Lagrangian fibrations, just not rotate these moduli spaces, stick with the Higgs bundle versions of them, since under this hyperkaehler rotation is diffeomorphic anyway, and then try and compute some topological invariance of the Higgs bundle moduli spaces, say for SLR and PGLR. That's exactly, again, what Hausel and Thaddeus were doing. And the reason you want to work on the Higgs bundle side and not in this part where you have flat connections is that Higgs bundles have the C-star action. Again, you can use Morse theory to compute topological invariance. And actually, from this sphere, you can see the origin of the C-star action. There's actually an S1 action or a C-star action that rotates the sphere and literally takes one complex structure here to another complex structure lambda here. And so these moduli spaces are not fixed under the action of C-star unless you're at the poles, which are precisely the Higgs bundles. So that's where these, you can think of the C-star action as originating in the hyperkaehler geometry. But yeah, so here we have the C-star action, which is an important algebraic tool for carrying out these kinds of calculations, which in a sense are motivated by mirror symmetry. Then the correct test, just strictly speaking, should be a comparison of so-called stringy E polynomials for the mixed Hodge structures of these moduli spaces. Not really you won't see any useful comparison by comparing their Poincare series. Again, this is in Hausel Thaddeus and other papers. Okay, so I guess in conclusion, the moduli space of Higgs bundles is quite a fascinating object. It's a solution space to gauge theoretic equations. It's a dynamical system in and of itself. And it's a hyperkaehler manifold with multiple moduli interpretations at once. And is a Calabi-Yau manifold with mirror symmetry. So this is an important object in geometry, representation theory, and physics. And as such, it's received quite a lot of attention. So I can give a very, very incomplete list of work that's in different directions has been done over the past 2 or 3 decades on Higgs bundles. Again, I have to emphasize this is incomplete. There's a lot of names missing from this. It's just to try and give you an idea for how much work is going on in this area. So there's this aspect of non-abelian Hodge theory where we have maps between Higgs bundles, flat connections or local systems, and representations of fundamental groups. This is the Dolbeau, Betty, and de Rham correspondence, if you like. So it was originally developed by Hitchin and then generalized by Donaldson, Corlett, Simpson, and Simpson, Yau, and Bolch in the non-compact case, and more recently Mochizuki. So this is a very difficult, hard sort of theory, but which paints a very pretty picture about how many different objects link together. Because we can use this to study fundamental groups, so there's this work on various on surface groups using Higgs bundles by Bradlow, Garcia Prada, Goten, Munoz, and others. And then again, there's a lot of work into computing the topology and also cohomology rings of these moduli spaces. Again, there's Hitchin, Goten, Hausel, Garcia Prada, Heinloth, Schmidt. There's also Mozgovoy and Schiffman, who I mentioned. I've snuck my own initial there. That's where most of my own work with Higgs bundles comes in. There's the parabolic Higgs bundles I mentioned, where you have holes, punctures in a surface, and you have holes in the Higgs field. So there's the tame case and the wild case, where you have higher order poles. So there's Bodin, Yokogawa, Picard, Bolch, Logaris, Martins, and many others. I mean, this has its own life in the physics world, and so there are many, many, many papers about this. And the wild Higgs is sort of an emerging topic. There are the so-called mixed type braids. So we have 3 complex structures, I, J, and K. So you can have submanifolds that are complex with respect to one structure, but symplectic with respect to another. So you have A, B, A, B, 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 brains, and so on. So this is recent work by Baraglia, Shapoznik, Biswas, Heller, Shapoznik on classifying these. And then there's the hyperkaehler metric, which I referred to as kappa earlier. So we know that this exists. So in a sense, the moduli space of Higgs bundles arises not only as a Kähler quotient, but as a hyperkaehler quotient. This is a quotient of Hitchin, Karlby, Lindstrom, and Rocek, which tells you if you start with a flat space with a hyperkaehler structure and you take the quotient, then you can get a non-trivial hyperkaehler manifold, and that's how the Hitchin system arises in one sense, but that's an existence result for the hyperkaehler metric. What is it actually? Can you write down the hyperkaehler metric? So that's a hard question, but recently there have been some answers. So there's the work of Gallardo, Moore, and Knightsky, and also Matsaya, Swoboda, Weiss, and Witt, and more recently Laura Fredrickson, where they study the asymptotics of the Higgs bundle moduli space. They go out to infinity in space, partially compactify it with something called limiting Higgs bundles or limiting configurations. And the result of this is that they're able to compare the hyperkaehler metric, at least over a kind of generic locus in the Hitchin base, where the characteristic polynomial has separated zeros. Compare the hyperkaehler metric there to the so-called semi-flat metric, which is another hyperkaehler metric, just not the one that comes from the quotient. But they're very, very close. So I believe that the error between them decays exponentially if you talk to the physicists, and as a polynomial if you talk to the mathematicians. Okay, so they're trying to bridge the gap, I think, between those two calculations. And then more recently, well, the topological recursion itself isn't so recent, but it's been applied to Higgs bundles very recently. So this is work originating in Maynard and Oranton, and the Higgs bundle perspective, partly due to Dimitrescu and Molazzi. And so you can compute Gromov-Witten invariance and other invariants using spectral curves and topological recursion for those curves. And then there's the geometric Langlands program, is very much related to the moduli space of Higgs bundles. So you have these people, Valence and Grudenfeld, Arinkin, Frankel, Denagi, Pantev, Nadler. It's a long list, Bensby, someone else who should be there. Finally, there's the fundamental lemma from also from the Langlands program, proven by Ngo, Lamont also contributed heavily to this. That's one of the real success stories of the theory of Higgs bundles, in fact, quite outside the origins of Higgs bundles. So in this argument, the affine-Springer fibration appears, and it turns out that the Hitchin fibration is a natural compactification, fibrowise compactification of the affine-Springer fibration, and that's the key to unlocking this. So sort of a success story, I think. Some magazine had called it one of the greatest scientific sort of successes of 2008 or 2009, something like that. So, so I think that's all I want to say. So, if I've convinced you about how great Higgs bundles are, you may want to own some for yourself. So you can buy Higgs bundle moduli spaces online. So this is a real slice of I guess a tame Higgs bundle moduli space on P1. These are made by Tomasz Hausel. So these are 3D printed, and you can buy them online. So this is, mind you, this is Canadian dollars, which are not worth as much as American dollars. So the price in US dollars is less than this. It's not exactly $300. You will have savings if you buy it in your own currency. And if you don't like this one, they have different finishes. That's the same price. The black one's a real steal. It's only 196 Canadian. So you can get them from that website up there. And I should say, I make no profit from this. I'm just pointing it out. So I don't see any of this. I have nothing to do with these. But they are there if you want them. You can buy Higgs moduli spaces. And I think that's everything.
Questions? Comments?
Can you see the vibration in the Pi model?
Not really. Like in these models, no. As I say, it's a real slice from a piece of the So they took some locus in the moduli space and then took a real slice, and then this is what you see. I mean, I think there are some fibers coming together here, but you can't really see the vibration structure, unfortunately. This is better for the vibration.
So what is the go back to the toy model? What's the Hitchin system?
What is the?
What is?
I believe this is a Hitchin system on P1 with punctures.
How many punctures?
I don't know how many punctures.
But it's P1 with 10 punctures.
10 punctures. Yeah. Some number. It's probably 4, if I had to guess. 4 is the toy model that everyone always has.
When you say cohomology, the moduli space, is that what kind of cohomology? Cohomology with complex support or?
The rational cohomology.
Rational cohomology.
Yeah.
How about the L2 cohomology?
The L2 cohomology, that's also, there are lots of open questions about it.
Yeah.
But I'm not sure, I mean, there are different techniques. I mean, the papers of Housel mostly go through are probably the best reference for the L2 cohomology, because there's Sen's conjecture in the context of Higgs bundles. So that's
By the way, is Sen's conjecture proof now or not?
I'm not sure. I mean, in the context of Higgs bundles, I'm not sure.
He was talking about monopoles, right? Moduli.
Yeah.
Was that proof?
For the monopoles, I'm also not sure. That's the original.
Probably for k equal 2 only.
Probably, yeah. But I don't think that you can use the C star action to get much information about it. So you have to sort of use other techniques.
C-star action cannot work for L2 cohomology.
At least you don't get as much information about the L2 cohomology as you would for the rational cohomology.
More questions? If not, let's thank speaker again.
So what you do is you can buy it online.
Yeah, you can buy them from that site, shapeways.com.
Why is it so expensive? How much? I mean, what kind of materials?
I don't know, but I guess probably just plastic.
Huh?
I think it's laser printed, so probably some form of plastic, but they finish them in different ways. Yeah. I haven't bought one myself, but I think I will at some point.
Where is the singularity? You can understand singularity?
In the case where rank and degree are not coprime? Yeah, because, well, I mean, in simple cases, yeah. If you have, say, a semistable bundle that looks like L plus L prime, let's say they're both degree 0.
Yeah.
Then, in principle, this is, Jack 0 x cross Jack 0 x together with the space of Higgs fields, but there's a Z2 action on this, so you get orbital points that way. This is the simplest example I can think of, but they get more complicated than this.
Is it always open for singularity?
I think when the rank and degree are not coprime, they're always orbital singulars. And I don't think they're worse than that, at least not on a Riemann surface. Thank you.
一个人是吧？
可以。
这个城在哪里啊？这个英国写什么
Saskatchewan 在明尼苏达上，
明尼苏达，那不会很冷。
很冷，比明尼苏达还冷。
啊？比明尼苏达还冷。